I am Sushmita from Sri Venkateshwara College of Engineering, Computer Science Department. Today's subject is operating system. So the topic is power savings through overloaded RTOS on multi-core architectures. So how can we power save using the operating systems we are going to see. In this, changes in computational demand have a huge impact on the evolution of the world on embedded systems, which is why multi-core architectures are quite reasonable as they strive to bring in enhanced performance but at the same time pose challenges on how to effectively exploit the resources. Continuing further into this subject, it describes a more elegant way of utilizing system resources through taking the RTOS away from the other cores and placing it into a dedicated course and studying this concept as means to achieve larger batteries within multi-core architecture. So using multi-core architecture we can achieve a larger batteries by studying this concept. So first, overloaded RTOS on multi-core process. So how does this overloading RTOS work on the multi-core processes? So there are three types of cores, that is execution core. In execution core, a separate core is provided for RTOS operations, making it free of any application workload and therefore its effect on the performance is diluted. So the separate core is provided for this RTOS in execution core, so making it free for any applications. And next is inter-core communication. In inter-core communication also takes place between this RTOS core and the application cores, where the application cores are created in the execution core and data transmitted between them is conducted with the innovation of task from any of the cores. So the data transfer, the communication is taking place between the RTOS core and the application core. So that the data from that transmission are conducted with the innovation of some other cores. Let's see what is application cores. Application core access application workload and increase overall performance due to additional resources that overloaded away from the application by the RTOS. So this application core or access application overloaded and increases the overall performance including that execution core, intercommunication core. So due to additional resources the overloaded away from the application run by the RTOS. Next one is benefits of overloaded RTOS for power savings. For power savings we are using RTOS using multi-core. So what are the benefits of that? So reduced core utilization. So we are utilizing very less amount of core, that is the RTOS being offloaded consumes less. So here the RTOS is offloaded, so the consumes less power from the application cores as they no longer need to handle RTOS related tasks. They no need to handle the task related to RTOS, so it consumes only less power. This significantly reduces overall power consumption. So here it significantly reduces overall power consumptions. Next, optimized DVFS and sleep modes. So in this offloading, the RTOS allows for more effective dynamic voltage and frequently scaling and sleeping mode utilization for application. So for application cores, the sleeping mode is there. So where we can use the sleeping mode and we can save the power, further enhancing power savings. So it allows for more effective dynamic voltage and frequency scaling and sleeping mode utilization also. Next one is power gating of unused cores. So if the core is not used, we can do the power gating. So with the RTOS on a dedicated core, unused application core can be effectively power gated, leading to substantial power reductions, especially during periods of low workload. So whenever we have a low workload or we don't want to use that core, we can do power gating. The power gated system can be used efficiently in the unused application cores. So here we can see the graph, that is offloaded RTOS, how it varies. So this is RTOS and this is the limitations. So here we can see the graph. And next one is challenges in implementing offloaded RTOs. So we found that offloaded RTOs we can implement. So what are the challenges are there to implement that? So first is inter-core communication, ensuring efficient and reliable data exchange between RTOS core and the application core. So there should be an efficient and reliable data. There should be a perfect data exchange between that RTOS core and application core, as we saw before. So maintaining real-time performance and avoid bottlenecks. So it should be an real time, it should maintain a real-time performance. So this should be ensured first. Then this is one of the challenge. So then task scheduling. Sophisticated scheduling algorithms are required to manage task execution across multiple cores, considering real-time constraints and optimizing resource utilization. So this scheduling, we have to schedule a perfect algorithm for this task to manage task execution across multiple cores. So we have to manage all the execution cores along the multiple cores, and execution across the multiple cores. So we need to manage that. That is one of the challenge. And the next one is memory management. So efficient memory allocation and management are essential to avoid resource contention and ensure the smooth operation of the RTOS and application tasks. So memory management. So we need a memory for doing this. So we have to manage the memory. So efficient memory allocation should be efficient to manage all the application tasks by the RTOS. And next one is real-time constraints. So what are the real-time challenges is maintaining real-time guarantees for critical tasks across multiple cores while ensuring power efficiency presents a significant challenge. So maintaining a real-time guarantees presents a significant challenge, as it is a critical task across. So doing the same thing in multiple cores is really a critical task. So ensuring power efficiency. So maintaining real-time guarantees is one of the significant challenges. So the next topic is architectural considerations for power efficient offloaded RTOs. So what are the consideration we need to do in this? Here, core how we can implement by considering this. So first one is core selection. It is important to make the right choice of core when it comes to RTOs. For example, a simple, efficient, low power core can be sufficient for the application core to concentrate more on processing demanding tasks. And next thing we have to consider is interconnect architecture. Appropriate interconnects among the RTOS core and the application core are needed for quick and efficient communication. The use of advanced interconnection structures such as AMDA or AXI improves performance. So this is the next consideration. So next thing is memory hierarchy. So an appropriate memory hierarchy such as cache memory and memory management unit has to be put in place to enhance access to data as well as reduce power consumption in the course of data movement. Next thing is peripheral integration. It would be reasonable to implement peripheral inside RTOS core to reduce the communication overhead as well as the power required to perform device tasks. So these are the consideration we need to do when we are implementing the offloaded RTOS. So the next topic is workload partition and task scheduling for power optimization. So how can we partition this? So for power optimization, how can we divide the things? First one is workload analysis. The phase is studying the workload of the application in question. The workloads are participated according to computational requirements, latency constraints and communication cost. Next one is task partitioning. Processing this information is dependent on the core specification. Tasks heavy on power technology parameters go to application cores, while those lean to RTOS related tasks stay on the RTOS core. And the next one is dynamic scheduling. Dynamic scheduling research techniques are implemented for moving tasks to specific cores as overloaded changes. This is done in order to improve performance while minimizing power consumption. So let me conclude this topic now. So conclusion and future research direction. Offloading the RTOS to a dedicated core in multi-core architecture presents a compelling approach to unlock significant power savings. The benefits include reduced core utilization, optimized dynamic voltage and frequency scaling, and the ability to power gate unused cores. However, challenges existing in inter-core communication, task scheduling, and ensuring real-time guarantees. Future research direction focus on developing more sophisticated intercore communication protocols, adaptive scheduling algorithms, and integrating AI-based techniques for dynamic optimization. Thank you for watching. Do like, subscribe.